Hello students, welcome back. In our previous part, we discussed about the nucleophilic substitution reactions of alkyl halides. So in this part, we are going to discuss about the remaining chemical properties of alkyl halides, that is the dehydrohalogenation reactions as well as the reactions with metal and other chemical reactions of alkyl halides. So let's start. So in our previous lecture, we discussed about only the nucleophilic substitution reactions, right? So now I am going to continue the remaining chemical properties, the remaining chemical reactions shown by alkyl halides. The second one is the dehydrohalogenation reactions. Dehydrohalogenation is nothing but elimination of HX, that is hydrogen halide. So when haloalkanes, when they are heated with alcoholic KOH, alcoholic potassium hydroxide, they undergo dehydrohalogenation to form alkenes basically. So when haloalkanes, when they are treated with alcoholic KOH, they undergo dehydrohalogenation, that is the removal of HX. HX is removed and will get alkenes as the products. So these reactions are called beta elimination because the hydrogen atom that is present typically at the beta position of haloalkanes. So the hydrogen atom that is present at the beta position of haloalkane, so that's why these are beta elimination reaction. So basically this dehydrohalogenation is an elimination reaction, right? So it's not substitution, it's completely elimination because one molecule is removed or one molecule is eliminated from the compound. So that's why it is dehydrohalogenation. So only the hydrohalogenation is the addition of HX. So it is dehydrohalogenation, nothing but removal of HX. So dehydrohalogenation reactions, if you see further, the reactivity of haloalkanes towards the elimination reaction follows the order. So always the tertiary alkyl halide will undergo elimination readily than the secondary. Comparatively, secondary is more as compared to the primary alkyl halide or haloalkane. So always remember that the tertiary will undergo elimination readily but not the primary one, because if you see, if the tertiary alkyl halide, if it undergoes dehydrohalogenation, then more substituted alkene is formed. Most substituted alkenes are formed as a product which are more stable and they are formed at a faster rate. Remember, like you might have studied in alkenes chapter, that is hydrocarbons, always the most substituted alkene is more stable, right, because of the hypoconjugation. So always the most substituted one is readily formed and is more stable. So these tertiary alkyl halides produce the most substituted alkanes. So that's why they are more reactive. And among the various halides with the same alkyl group, so if I don't vary the alkyl group and if I vary only the halogen atom, then the order of reactivity as follows. With the R, it may be methyl or it may be tertiary butyl or it may be isopropyl group. So that iodide is, alkyl iodide is more reactive because of the low bond dissociation energy of Ci bond. That's why it readily breaks and it easily undergo the reaction. Yeah, if you get into more details of this dehydrohalogenation, you can see this is an example of dehydrohalogenation. So in the case of haloalkenes, so then there is a possibility that more than two alkenes may be formed. Like you can see in this example where this is one I have taken, that is the 2, this is what? 2-butyl-2-bromo butane, right? So 2-bromo butane. So if when it is treated with alcoholic KOH and if I heat this mixture, then I will get two products. But only one of them is major. So one is 80% and other is 20%. So this is the major product. So here there are two possibilities. So let's see how these are formed and why the one is in major amount than other. So you can see it is elimination of HBr. So always H and Br are eliminated from the adjacent carbon atoms. So here it has, this is one hydrogen atom, and here also hydrogen atom is present, right? So this hydrogen along with this bromine can, this HBr may go out. So if this HBr go out, then you will get a double bond here. So that is this product. But if this HBr goes, this hydrogen along with this bromine is went out, so you will get alkene here. So this alkene is this one. So this is most substituted one. It is not terminal one, right? This is terminal one. It is not substituted. But this alkene is more substituted. So that's why this is major product and this is the minor product, because it is more stable one and is formed in the greater amount. Yeah, so we're done with the dehydrohalogenation, and let's move to the reaction with metals. So here we'll see the reaction with sodium and the reaction with magnesium, lithium and lead sodium alloy. So the reaction with sodium is known as Wood reaction. Wood reaction, which is a very, very important name reaction. So let's get into the details of these reactions. So first is reaction with sodium. So alkyl halide, upon reaction with sodium, they produce alkanes. This is the reaction. So this is alkyl halide. The 2 moles is reacting with the 2 moles of sodium and is producing alkane along with the 2 moles of sodium halide. So this reaction occurs in the presence of dry ether. This reaction occurs in the presence of dry ether, and you will get alkane as the product. But however, this reaction has a limitation. This is not suitable for the preparation of unsymmetrical alkanes. Like this is a symmetrical alkane, CH3CH3 or C2H5 C2H5. These are symmetrical alkanes. Both the alkyl groups are same, but this is not suitable for getting this product. Why? Because means here if I take 2 different alkyl halides, then there is a possibility that you will get a mixture of products, right? So if I take CH3X along with C2H5X, then I may get CH3CH3, that is this one. I may get C2H5, that is this one, or when these two react with each other, and I will get this one. So here I am not getting especially one product in major amount, I am getting a mixture of products. So if I want to prepare this unsymmetrical one, this method is not suitable, because you will get the symmetrical one also along with this unsymmetrical one. So here you will get a mixture, so it will be difficult for you to isolate. So if I want only this cross product in the major amount, then I should go for other type of reaction, not this one, because you will get a mixture of products, but we don't want that. So this is only suitable for preparation of symmetrical alkanes, that is one thing. And one more point which is important about this reaction is, so here I am taking dry ether, right? So but if I take moist ether, then alcohol would also be the byproduct. Here I am not getting any alcohol, but if I take dry ether, if I take moist ether which is containing the water vapor H2O, then this will react with the alkyl halide and it produces alcohol. So alcohol is also obtained as one of the byproduct along with the sodium halide, right? So this is the important thing about the Wood reaction, right? This reaction is known as Wood reaction. And let's see the reaction with magnesium. So the haloalkenes, they react with the magnesium in the presence of dry ether. Here also the solvent is dry ether to form the alkyl magnesium halide. So this RMgX is very, very important and special candidate in organic chemistry, that is known as Grignard reagent. Grignard reagent, that is RMgX, which is alkyl magnesium halide, which is formed upon reaction with Rx and Mg in the presence of dry ether. So the Grignard reagents, they are organometallic compounds. It is having metal and it is having the organic compound, that carbon and halogen. So it is an organometallic compound, and the compound which is having the metal carbon bond. So here this is the metal magnesium and this is the carbon. So it is having a carbon metal bond, and these are they are highly reactive compounds. They are highly reactive candidates, and they react with the proton donors and they give hydrocarbons as the product. So because this R minus, it will capture the proton from the acid and it will produces RH. Okay, so this is the reaction with magnesium. And if you see the third is the reaction with lithium. So the haloalkanes, they react with the lithium in the presence of dry ether. Here also the solvent is dry ether and they form alkyl lithium. So this is the alkyl halide. Upon reaction with lithium, it is producing alkyl lithium. Okay, so these also are strong bases. These are very strong bases because this is CH3 CH2 minus is a very strong base because its conjugate is a very weak acid. That the ethane CH3 is a very weak acid, so its conjugate base is a very strong base. And the fourth type of reaction is a reaction with the lead sodium alloy. So here I am taking a lead sodium alloy. So this is the lead sodium alloy. Upon reaction with the ethyl bromide, it produces a very important compound, that is tetraethyl lead. So this is the tetraethyl lead. Okay, so this is also very important. And now we are going to discuss about the reduction reactions. So the haloalkanes, upon reduction, they will form alkanes by any of the two following methods. One is by taking hydrogen in presence of nickel. So this is one reducing agent, and the reaction with zinc copper couple. So these two are the reactions, the reduction reactions of alkyl halide. So they yield alkanes as the product. So this is the simple reaction in fact. But if you take the second one, so in the presence of alcohols, the zinc copper couple, it reduces haloalkanes to alkanes. Okay, so the zinc copper couple, in the presence of alcohol, it reduces the haloalkanes to alkanes. So this is the reduction reactions shown by alkyl halides. And if you see the reaction with alkyl cyanide, so the alkyl halide, upon reaction with the potassium cyanide, let's suppose, it produces alkyl cyanide. So this RCN is the alkyl cyanide, so which upon complete hydrolysis produces acid. It produces acid, that is RCOOH. But if it is a partial hydrolysis, then the reaction will end up in producing amide, that is RCONH2. This is the amide, and this RCN can also undergo reduction and it produces amide. So this alkyl cyanide upon hydrolysis, that is the complete hydrolysis and partial hydrolysis, will yield different types of products, and it can also undergo reduction to produce other one. So which is one of the source to get different products depending on the type of reaction that you are using. So the next is the very important one, that is Williamson synthesis. This is also one of the important name reaction. So which is an organic reaction forming an ether. This reaction is forming an ether from organohalide and alcohol. So here if you see the reactions typically, this is the alkoxide ion, that is methoxide or ethoxide. So alkoxide ion, it will attack the primary alkyl halide via SN2 reaction. So this is a primary alkyl halide, so which is very reactive for SN2 reaction, and this alkoxide ion will attack this alkyl halide and it produces the ether. So this is the production of ethers. So that's why we can also call this synthesis as Williamson's ether synthesis, because it involves the production of ether. So this reaction is also it's important in the history of the organic chemistry because it helped to prove the structure of ethers, right? So this is also one of the important reaction in the organic chemistry. So these are the chemical properties of alkyl halides, the different kind of reactions shown by alkyl halides, starting from nucleophilic substitutions to the last one, reduction reactions and Williamson synthesis. So students, in this particular part we discussed about the dehydrohalogenation reactions and the reactions of alkyl halides with metals like sodium, magnesium, lithium, and we also discussed about one of the important named reaction, that is Williamson synthesis. So this is all about the chemical properties and physical properties and all about the alkyl halides. So in our next part we are going to discuss about the aryl halides, that is the second part of this chapter.